Hello? Okay, this is better. Right, so yeah, it's good that I'm talking behind the two previous talks, because this talk will be about subsequences and also will be about trees. So anyway, our task today is to compute this function h, which takes a list as its input, with the property that h of x's is defined in terms of the values of h on all the immediate sublists or subsequences of x's. And by an immediate sublist, I mean that a list of y's is an immediate sublist of x's if y's can be obtained from x's by removing exactly one element. Okay, so for example, to compute h of ABCD, we need the values of h of ABC, ABD, ACD, and BCD. And to compute the value of h of ABD, for example, we need the value of h of AB, AD, and BD, and so on. And if we compute in this top-down manner, you will see that we end up doing lots of recomputations. Like in this picture, h of AB is computed twice, h of AC is computed twice, and when the list gets longer, we will see more repetitions. So it will be preferable to have some bottom-up strategy, which computes the value of h level by level. So probably in the first level, we compute the value of h for all the sublists of length 1. And in level 2, we compute the list of h for all the sublists of level 2, and we keep going up like this until we reach the top. And so as a visual aid in this picture, dependency from the same value are drawn using the same color, but it's not essential to understand this talk. And so then you might imagine implementing this algorithm by representing each level as an array, and then to compute any particular value, you use some smart bit level index computation to find out where the values needed are in the previous level. But however, this bit level computation is not going to be as easy as it seems, and your code will not be pretty. I'm sure you're not going to like it. So instead, we are going to develop some data structure for this purpose today. And this algorithm, this problem was actually started by Richard Bird in one of his 2008 paper, and the purpose of that paper was to study the relationship between top-down and bottom-up algorithms. And this problem, Richard used to say that 3 examples make a paper. And this example was the last one in his paper. So in the algorithm, at the core of the algorithm he presented is a short function defined in 4 lines, which I couldn't understand at all. And it's very concise, looks pretty, but I couldn't even say clearly what this function does at all. And so and being the last example, Richard didn't want to spend too many pages on it. See, he simply presented it and claimed it correct. So I was looking at the algorithm and thinking, is it possible for me to understand this function or even to calculate it? And that's the motivation of this piece of work. Okay, probably time to get to be a little bit more formal. So this function subs takes a list and computes all the immediate sublists. The definition is standard. There's no immediate sublist for an empty list, and the immediate sublist for x axis is either x's or the sublist of x's with x attached to the left. Okay, so then our top-down function as a specification, our top-down function can be specified by 2 functions f and g. So for the sake of presentation, we are going to consider only non-empty lists in this talk and in the paper. So the base cases are singleton lists, and for which we apply the base case. In the base case, we use the function f to get the value we want. And for lists having at least 2 elements, we compute all the immediate sublists apply edge to all these all these sublists before collecting all the results using a function g, having type list of y to y. Okay, that should be very clear. And then what about the bottom-up computation? So how do we build one level from the previous level? The computation from one level to the next can probably be seen as a two-step process. So in this slide below is level 2, and above there is level 3. So you see, for example, to compute h of ABD, we need the values of h of AB, AD, and BD. And to compute h of ACD, we need the values of h of AC, AD, and CD. So if we can somehow construct a metric function, which I'm going to go upgrade, which takes level 2 and copies and regroups the value such that all the needed value are grouped together, then we just need to do a map of G to compute level 3. And now I'm going to call this middle level level 2.5. So if we can construct this function upgrade, which has type list of B to list of B, and the bottom-up algorithm would look like this, that we start with having a list axis. We start with doing a map F to compute level 1. And then we do map G after upgrade n minus 1 times, where n is the length of the list. And by the time you finish, there should be, at the top, there should be just a singleton list whose value you can extract. Okay? Right. So now the problem is to construct this function upgrade. But what does it do, actually, anyway? We had to build the function, we need to have a clear specification. So can we write down formally what it does? To do that, to talk about what it does, we need to talk about this function choose, which takes a natural number k and a list called axis and gives you all the way to choose k elements from the list axis. And the definition is also standard. So there's one way to choose 0 elements from a list, which is the empty list, and to choose 1 plus k elements from xcons axis, for example. We can either keep x and choose k elements from axis, or we can drop x and choose 1 plus k elements from axis. And this function choose returns a list of A, so the results of these two recursive calls are just appended together. Let's choose, which is also standard. Okay, now that we have choose, we realize that the level 2 is actually the result of map edge after choose 2, and level 3 is actually the result of map edge after choose 3. And what about the level 2.5? If we can say clearly what it is, then we have a specification for upgrade. But what is it? Right, upgrade should be a natural transformation. So if we just forget about edge, then this level 2.5, what is level 2.5? So ABACBD is actually the sublist of ABC. ABADBD is actually the immediate sublist of ABD. So actually, we get level 2.5 from level 3 by doing a map subs. And here we have our specification. This is what upgrade does, basically. So upgrade is a function take from a list of B, list of anything, list of B to a list of B. And when it's given level K, it returns the list of B, which should look like applying map of subs to level 1 plus K. And there are some other side conditions on on k and the length of axis, which we can ignore for this talk. And presumably now we have a specification for upgrade. We should be able to calculate it by what? Okay, by induction, basically. Or the function choose have 3 cases, so you should be able to expand the 3 cases and do some transformation, try to find out what upgrade should be to allow you to go from the left-hand side of the equality to the right-hand side. Then you should be able to construct this function upgrade. If you do that this way, you are going to fail at one point, because at one point you are going to realize that representing the level, each level in lists, drops too much information. You need some other data structure which kind of remembers how the choices were made in choose to allow you to proceed. So instead of lists, we use some kind of tree. And this type B of A is just a tip-valued binary tree. It's a binary tree having values on the tip only. So B of A is either a tip, T of A, having a value A, or a node having 2 subtrees. And the tree version of choose, which I'm going to call CH, looks almost like the previous function choose, with one difference that it returns a B of list of A rather than a list of A. And in the last case, rather than doing an append here, you keep the 2 branches keep the 2 results of your recursive call in the 2 branches of the binary tree to remember where it comes from. So I'm going to show you some, okay, and also once we introduce the tree, we naturally have a function map for it, and another function zip bwidth, which zips 2 trees having the same shape together using a function a to b to c, right, which we're going to use later. Okay, so I'm going to show you some examples. So later on the slides, a tip is just going to be drawn as by its value, and a node having 2 subtrees are going to be drawn like that. The right subtree, the left subtree will be at the bottom. The right subtree will be drawn on the right. Right. Okay. Yes. So this is what happens when we do choose one of ABCD. It's just like a list, and this is our level 2, which we can compute by choose 2 of ABCDE. Then you can see that in the left subtree are all the choices having A, and in the right subtree are all the choices not having A. And again, in the right subtree of the left subtree are all the choices having B, and then this tree are all the choices not having B. And this is level 3. And another thing you will notice is that this subtree, these 2 subtrees have the same shape. Why is that? Yes, of course, because we compute the tree on the top was computed from by attaching an A to every node of this tree. So of course they have the same shape. And so basically, the tree follows a certain structure. It's not just any binary tree. So you might be thinking using dependent type to put more constraint on the shape of the tree to make things clearer, which is a good idea, but that will be a separate paper. Okay, so right, and then actually, if you compute these sizes of all these, if you compute the size of every subtree in the tree, you see this sequence of number. So in here you have from right to left, you have 1, 2, 3, 4. You have 1, 3, 6, 10. Here you have 1, 4, 10. Does that look familiar to you in any way? This is, sorry? This is actually the diagonals of Pascal triangle, which is, the first time I saw it, I was surprised, but actually now that looking back at it, it's not as surprising because Pascal triangle is very closely related to choose anyway. So, okay, anyway, back to our problem. So now the new specification of the function up is something like this, that each levels are now presented as trees. So up takes level k and produce a tree of lists, which should look like applying MACB of subs to level 1 plus k. And now you can calculate up. It's a pity that I cannot show you the calculation due to time constraints, but it's probably for the best because it's more fun if you try it yourself. And I do invite you to try it, and if you are interested, take a look at the calculation in my paper. You know, the point of writing a functional Perl is that I find something fun, so I want to share with people, and so let's try this together. But anyway, now, so for now, I'm going to just to show you the result of the calculation, which is this 4-line function. That's the function in Richard's paper that I saw, which confused me. And still, it doesn't it still looks mysterious. But however, now we have a specification and a calculation toward this function. So to show you how it worked, okay, now there are 4 cases. To show you how this function works, let's see an example. So now at the bottom, this is level 2. And this orange dot is where we are at. So we start from the root, and it matches the last branch of the function. So we will go all the way to the right until we reach this tree. And what is matched are the first 2 cases. The 2 middle cases, the first 2 cases of the function. And I'm going to skip the details and just tell you that given this tree, all the 3 nodes collapse into 1 node, which gives the result is 1 node having 3 things, CD, CE, and DE. And then we go back a bit, and now to the parent, and then go down to here. Then we go back a bit and to this subtree. Right, so now what's matched is the 3rd case, the third case, this one. And so now this is Y, this is U. And what should we do? It says that we should do, okay, this node is the result of up of U, which is collapsing to 1 node, BD, BE. Then you get this subtree by taking U and attach BC to both of them. That's why you get BC, BD, BC, BE. Okay, right. And we do one more step. So yeah, this is what happens when you apply that tree to when you apply up to that tree. And now when we are considering here, now it's the last branch, it's the last case being matched, and the 2 trees T and U are drawn drawing this in the dotted square. So what we should do now is, according to the definition, is to compute up of T and then zip this with U. And why can we do that? Because they have the same shape. So then after zipping this tree with this tree, we get the tree there having BC, BD, CD, BC, BE, CE, BD, and BD, BE, DE, and so on. And then now finally back here, we do the same thing again, zipping that tree whose construction I'm omitting with that tree U, and that gives you the a tree containing subsequences, immediate sequences of ABC, ABD, ABE, and so on. So that's basically how the algorithm works. And that's it. So then that's how you construct level 3. Okay, then I'm going to stop here. Thank you. Please.
I was wondering what's H? We have a black marker. I don't think so. I was wondering what
Thank you, sorry.
Yes. You can go first.
I was just wondering what H's, what are some H's that we might care about?
Actually, it's been hard to find useful examples. So I asked some friend of mine doing, because probably the question can be rephrased as what's the use of application for this. And I asked some of my friends doing algorithms, then they say that in their circles, he said, it's a common pattern they see often, and actually many problems on sequences, for example, some form of minimum editing distance problem can be rephrased into problems of this shape. And he explained that to me, and I believed him. Then now I forgot. So, however, for me, it's just a fun exercise. Thank you.
Yeah, thank you for your talk. So I hope I understood this correctly, but I think when you're going from level 2 to level 3, you have like this whole subtree that starts with the A's that you're no longer using, right? Because there's nothing you can put on front of it.
Sorry? Oh, the A's I'm not using.
So I think you are.
So, yeah. Yes. So this is the last step of constructing level 2 from level 3, and then this tree T is transformed into this, having ABAC, ABAD, and so on, and then it has the same shape of this as this tree, so they can zip together to form this. And indeed, every values are still there.
Okay. Yeah. Thank you.
Thank you.
So my question is something along the lines of, if the order of the immediate sublists doesn't matter, is there any extra performance juice you can squeeze out of it? Because it seems that some effort goes into maintaining everything the same order as you would get with the naive top-down thing.
So you're asking, if the order of things in the sublist doesn't matter, could there be a quicker algorithm for this? I don't know, actually. However, we are maintaining the shape there is mainly to allow us to do this transformation, to put everything in the right place. And now for me, the elements being in the right order seems to be a side effect. Mm-hmm. And yeah, but that's a good question. Thank you. Okay.
Thank you for your questions, and thanks you for your talk. Let's thank Shin-Cheng again.